Look up at the night sky on a clear, dark evening. What do you see? A vast, silent canvas speckled with gentle, twinkling lights. For millennia, humanity looked at those distant points of illumination and saw gods, mythical heroes and omens. But the truth is far more violent, far more chaotic, and infinitely more fascinating. Every single one of those seemingly peaceful dots is actually a colossal, roaring nuclear reactor suspended in the freezing vacuum of space. They are the ultimate engines of the cosmos, burning with unimaginable fury, crushing matter together under extreme gravity to forge the very building blocks of reality. Without these blazing celestial engines, the universe would be nothing more than a dark, freezing ocean of drifting hydrogen gas. There would be no carbon for biology, no oxygen to breathe, no iron for our blood, and no solid planets to stand on. Everything we are, everything we know, was cooked inside the boiling heart of a star. Today, we are going deeper into the cosmos than ever before. We are going to tear apart the mechanics of reality to understand stars, the engines of the universe. We will explore how they are born from chaotic dust, how they fight a lifelong brutal war against their own gravity, and how their spectacular deaths seed the galaxies with the elements necessary for life. Before we ignite this journey, if you are passionate about exploring the deep mysteries of space and science, consider hitting the like button and subscribing to the channel. I also want to know exactly who is riding along on this cosmic expedition with me today, so head down to the comments right now and tell me where in the world you are watching from and what time it is there. Are you sitting under the morning sun or looking up at the midnight stars? Now, let us leave the safety of our pale blue dot, travel millions of light years across the infinite void, and stare directly into the raging fires of creation. To understand how the greatest engines in the cosmos roar to life, we must travel back to the very beginning of the stellar life cycle. We must venture into the quietest, darkest, and coldest realms of the interstellar medium. Out in the vast expanses between existing star systems lie colossal structures known as giant molecular clouds. These cosmic nurseries stretch across tens or even hundreds of light years. They contain enough mass to build hundreds of thousands of stars the size of our sun. Yet, when you look inside one of these clouds, you do not see fire, heat, or violent explosions. Instead, you encounter an immense, freezing desert of gas and microscopic dust particles. The temperature inside these molecular clouds drops to absolute extremes, hovering just 10 to 20 degrees above absolute zero. At these frigid temperatures, matter slows down to a crawl. Atoms can cling together without being ripped apart by thermal agitation. The primary ingredient filling these deep voids is hydrogen gas, existing mostly in molecular form, where two hydrogen atoms bond tightly together. Helium atoms drift among them, making up nearly all of the remaining gas. Tiny specks of silicate dust, carbon soot, and frozen water ice make up only a tiny fraction of the total mass, but they play a crucial role by absorbing background starlight and keeping the interior of the cloud impenetrably dark and cold. In this frozen environment, a delicate, silent war is constantly taking place. It is a fundamental duel between two opposing forces of nature: thermal pressure and gravity. Thermal pressure is the outward push caused by the kinetic motion of the gas molecules. Even in a cloud near absolute zero, the molecules jiggle and collide, exerting a gentle outward force that tries to disperse the gas into empty space. Opposing this expansion is universal gravity. Every single atom of hydrogen, every particle of helium, and every grain of dust possesses mass, and therefore exerts a gravitational pull on every other particle in the cloud. Gravity wants nothing more than to pull every atom inward toward a common center of mass, crushing the entire cloud into an infinitely dense point. For millions of years, giant molecular clouds can remain in a state of fragile equilibrium. The gentle outward push of thermal pressure perfectly balances the inward pull of gravity. The cloud remains stable, dark, and dormant. But this peace cannot last forever. To ignite a star, something must disrupt the balance. Something must tilt the scales in favor of gravity. This disruption often comes from external violence. A nearby massive star might end its life in a cataclysmic supernova explosion, sending a supersonic shockwave rippling through space. When this wall of compressed energy slams into the molecular cloud, it plows through the gas like a cosmic snowplow. In other cases, the gravitational wave from a passing star, the collision between two different clouds, or the sweeping compression of a galactic spiral arm can deliver the necessary jolt. When this happens, the density in localized pockets of the cloud spikes dramatically. The gas is squeezed together. The distance between individual atoms shrinks. Because gravity strengthens exponentially as objects get closer together, the inward gravitational force within these compressed pockets suddenly overwhelms the weak thermal pressure. The gas passes what astrophysicists call the critical mass threshold, often referred to as the Jeans mass. Once this threshold is crossed, the pocket of gas loses its ability to support its own weight. The cloud can no longer resist. It begins to collapse under its own gravity. What follows is an astronomical chain reaction. The cloud does not collapse as a single uniform sphere. Instead, it fragments into dozens, hundreds, or even thousands of smaller, denser clumps. Each clump becomes an independent pocket of runaway gravitational collapse, destined to become an individual star or a multiple star system. As one of these dense cores begins to fall inward, the physics of thermodynamics takes center stage. In the earliest stages of collapse, the falling gas can easily radiate its energy away into space through long-wavelength infrared light. The gas stays cold, allowing gravity to accelerate the infall of matter without any rising thermal pressure pushing back. This is known as the isothermal collapse phase. However, as hundreds of thousands of times the mass of the Earth continues to rush toward the center, the core becomes increasingly crowded and dense. The gas grows thick, and the interstellar dust grains pack together so tightly that infrared radiation can no longer escape freely. The heat becomes trapped inside. With heat trapped, the physics fundamentally shifts. The core transitions from a cold, isothermal state to an adiabatic state. The temperature and pressure inside the core begin to climb exponentially. The falling molecules collide with incredible frequency and violence. The gravitational potential energy of falling matter transforms directly into kinetic thermal energy. What was once a frozen pocket of space near absolute zero begins to warm up, rising to hundreds, then thousands of degrees. At the very center of this collapsing envelope, a distinct object begins to form, a protostar. The protostar is not yet a true star. It is not generating energy through nuclear fusion. Instead, it is an infant celestial body shining purely from the heat generated by gravitational contraction. It is an embryonic sphere of dense, glowing plasma, still buried deep inside an opaque cocoon of gas and dust. Because the original molecular cloud possessed a tiny amount of natural rotation, the conservation of angular momentum begins to dominate the system. Just as an ice skater spins faster and faster when pulling their arms inward, the collapsing gas begins to spin with increasing speed as it falls toward the central protostar. The gas cannot fall directly onto the surface of the protostar because the centrifugal force prevents material along the equator from collapsing straight inward. Instead, the infalling gas and dust flatten out into a vast, swirling disk rotating around the protostar, known as a circumstellar accretion disk. Gas from the surrounding envelope falls onto the disk, spirals inward through friction and magnetic turbulence, and gradually feeds onto the growing protostar at the center. Meanwhile, powerful magnetic fields twisting around the rotating core channel a portion of the incoming matter toward the poles, blasting it into interstellar space as two colossal, highly collimated jets of supersonic gas. These stellar jets carve immense cavities into the surrounding cloud, signaling to the universe that a new engine is assembling its parts. Over hundreds of thousands of years, the protostar continues to feed hungrily from its accretion disk. Its mass swells, its gravity intensifies, and the pressure at its core reaches levels beyond human comprehension. The atoms at the center are stripped of their electrons, creating a chaotic soup of bare atomic nuclei and free electrons. The core temperature surges from thousands of degrees into the millions. The engine is fully assembled, fueled by vast reserves of hydrogen, and compressed by the relentless weight of entire worlds falling upon it. The final spark of ignition is now only a matter of time. To understand what truly transforms a collapsing cloud of gas into a roaring, self-sustaining celestial powerhouse, we must plunge deep beneath the glowing outer layers of the newborn star and journey all the way to the heart of the machine. Here, deep in the stellar core, we enter an environment of sheer physical extremity that defies everyday human experience. The weight of an entire world, hundreds of thousands of times the mass of Earth, bears down relentlessly on this central zone. The density rises to levels where a single cubic inch of matter weighs more than a locomotive. The temperature climbs past 1 million, then 5 million, and finally surges past 10 to 15 million degrees Kelvin. Under these brutal conditions, atoms can no longer maintain their basic structural integrity. The energetic collisions are so violent that orbital electrons are completely stripped away from their atomic nuclei. The matter dissolves into a searing, hyperdense soup of bare subatomic particles known as plasma. Free electrons zip through space alongside naked hydrogen nuclei, which are simply solitary protons. At first glance, classic physics suggests that these protons should never be able to touch one another. Every proton carries a positive electrical charge. According to the fundamental laws of electromagnetism, like charges repel and opposite charges attract. The closer two positively charged protons get to each other, the more violently the electrostatic repulsion, known as the Coulomb barrier, pushes them apart. Even at temperatures of 15 million degrees, where protons are darting around at speeds of hundreds of miles per second, classical calculations show that their kinetic energy is simply not high enough to overcome this immense electric shield. Under the strict rules of classical mechanics, two protons colliding head-on in the core of a star would bounce off one another like billiard balls. If classical physics were the only law governing the cosmos, stars would never ignite, the universe would remain pitch black, and we would not exist. To light the stellar fires, the cosmos relies on the bizarre, counterintuitive laws of the subatomic realm, quantum mechanics. In the quantum world, particles do not exist at single, perfectly defined points in space. Instead, every particle, including the proton, behaves simultaneously like a particle and a wave of probability. A proton is described by a mathematical wave function that represents the likelihood of finding it at any given location. Because this wave function is spread out across space, the edge of the probability wave can actually extend straight through the electrostatic barrier. This introduces a phenomenon known as quantum tunneling. When two high-speed protons collide in the scorching heart of a star, there is a tiny, non-zero probability that a proton will spontaneously bypass the Coulomb barrier without ever possessing the classical energy required to climb over it. It is as if the particle simply vanishes from one side of an impenetrable wall and instantly materializes on the other side. Because the probability of quantum tunneling for any single collision is extraordinarily low, an individual proton might bounce off its neighbors billions of times over billions of years before successfully tunneling. But inside the hyperdense core of a star, there are countless octillions of protons packed into a confined space, colliding trillions of times every single second. Through sheer statistical volume, quantum tunneling occurs continuously, allowing atomic nuclei to come within reach of a much more powerful, short-range interaction, the strong nuclear force. Once quantum tunneling brings two protons within approximately 1 femtometer of each other, the strong nuclear force takes over. This fundamental force is hundreds of times stronger than electromagnetism, but it only operates across microscopic subatomic distances. It acts like an irresistible nuclear superglue, snatching the two protons and locking them together. In stars like our Sun, this initiates a multi-step nuclear dance called the Proton-Proton chain reaction. In the very instant two protons fuse, another fundamental force, the weak nuclear force, plays a crucial role. One of the protons spontaneously undergoes beta decay, converting into a neutron while spitting out a positron, the antimatter twin of an electron, and an elusive, nearly massless particle called a neutrino. This newly formed pair of one proton and one neutron constitutes a stable nucleus of heavy hydrogen, known as deuterium. The positron immediately collides with a nearby free electron in the dense plasma, annihilating both particles instantly and releasing a burst of high-energy gamma-ray radiation. Meanwhile, the newly created deuterium nucleus survives for only a fraction of a second before colliding with yet another ambient proton. They instantly fuse to create an isotope called helium-3, accompanied by another flash of pure gamma-ray energy. The final step of this dominant branch occurs when two helium-3 nuclei, forged in separate reactions throughout the core, smash into one another. When they fuse, they undergo a violent structural rearrangement, creating a single, extremely stable helium-4 nucleus consisting of 2 protons and 2 neutrons, while ejecting 2 energetic surplus protons back into the surrounding plasma to continue the cycle. This is the alchemy of the stars. 4 individual protons have been systematically crushed and assembled into one single helium-4 nucleus. But the real magic of this transformation lies in the balance sheet of mass. If you take 4 separate, unbound protons and place them on an ultra-precise atomic scale, and then compare that total to the mass of the newly created helium-4 nucleus, you discover something astonishing. The helium-4 nucleus is slightly lighter than the 4 original protons that built it. Approximately 0.7% of the initial mass has completely vanished from the physical ledger. This missing mass has not been destroyed. Instead, it has been converted directly into raw, radiant energy, governed by the most famous equation in modern science. Energy equals mass multiplied by the speed of light squared. Because the speed of light is an incomprehensibly vast number, approximately 300,000 kilometers per second, squaring that number produces a conversion factor of staggering proportions. This means that a minuscule, imperceptible fraction of a gram of mass converts into an enormous, explosive torrent of kinetic energy, energetic particles, and high-frequency gamma-ray photons. Inside the stellar core, this reaction does not happen in isolation. In a star like our Sun, the core fuses hundreds of millions of metric tons of hydrogen into helium every single second. In doing so, several million tons of pure matter vanish into raw energy each second, generating a continuous power output equivalent to the detonation of billions of nuclear weapons every moment. This colossal liberation of energy creates an intense outward radiation pressure, along with high thermal pressure from the superheated plasma. This outward blast of energy pushes violently against the surrounding layers of the star. It precisely counters the crushing weight of gravity that is constantly trying to collapse the star into a black hole. Astrophysicists call this perfect, delicate truce hydrostatic equilibrium. As long as the core has hydrogen to burn, the outward expansion, driven by nuclear fusion, and the inward crush driven by universal gravity, remain in flawless balance. The star becomes stable, resilient, and enduring. The quantum ignition is complete. The nuclear reactor is online, and the stellar engine begins its long, glorious lifetime of illuminating the surrounding universe. Once the nuclear engines at the core achieve steady hydrostatic equilibrium, a star enters the longest and most stable phase of its life. But the universe does not build its engines to a single, uniform blueprint. Just as an engineer can construct anything from a modest, fuel-sipping moped to a massive, roaring rocket engine, nature manufactures stars across a staggering spectrum of masses, temperatures, sizes, and luminosities. To make sense of this dazzling diversity, astrophysicists rely on one of the most powerful diagnostic frameworks ever devised in observational astronomy, the Hertzsprung-Russell diagram. When astronomers map stars on this revolutionary chart, plotting their surface temperature along the horizontal axis against their total energy output, or luminosity, along the vertical axis, a striking pattern emerges. The stars do not scatter randomly across the graph. Instead, roughly 90% of all stars align neatly along a continuous, sweeping diagonal band known as the main sequence. Along this primary highway of stellar evolution, every single member is engaged in the exact same fundamental process, steadily fusing hydrogen into helium inside its scorching core. To organize this stellar zoo, scientists developed the Harvard Spectral Classification System, which ranks stars by surface temperature using 7 primary letter designations: O, B, A, F, G, K, and M. Generations of astronomy students memorize this sequence through the famous mnemonic, "Oh, be a fine girl" or "Guy, kiss me." At the far right and bottom of this sequence, where temperatures are cool and brightness is modest, lies spectral class M. At the far left and top, where temperatures soar to blisteringly high levels and luminosities become blindingly intense, lies spectral class O. Let us begin our exploration at the bottom of the cosmic hierarchy, with the true workhorses of the universe, the red dwarfs or class M stars. These are the most common stars in existence, accounting for over 70% of all stars in the Milky Way galaxy. In terms of mass, they sit near the absolute lower physical threshold required for stellar ignition, possessing between 8% and roughly 50% of the mass of our Sun. Because their gravitational compression is gentle compared to their heavier siblings, red dwarfs have relatively low core temperatures and pressures. Consequently, their nuclear fusion proceeds at a slow, lazy, and highly economical crawl. Their surface temperatures hover between 2,400 and 3,700 Kelvin, causing them to glow with a deep, dull reddish hue. Their luminosity is so faint that not a single red dwarf is visible to the naked human eye from Earth, not even Proxima Centauri, the closest individual star to our solar system. Yet what red dwarfs lack in visual brilliance, they make up for with extraordinary longevity and unique internal mechanics. In larger stars like our Sun, energy from the core travels outward through an inner radiative zone before reaching a boiling convective envelope near the surface. But red dwarfs are fully convective throughout their entire interior. Heated plasma from the core rises all the way to the surface, cools slightly, and sinks right back down into the nuclear furnace. This continuous whole-star circulation means that a red dwarf constantly stirs its fuel tank, cycling almost every single hydrogen atom in its entire body into the core over time. While our Sun will exhaust its core hydrogen in roughly 10 billion years, a red dwarf burns through its reserves so slowly and thoroughly that it can live for trillions of years. That is hundreds of times longer than the current age of the universe. Long after every bright, massive star in the cosmos has exploded and died, the humble red dwarfs will remain quietly burning in the dark, the ultimate survivors of the stellar kingdom. Moving up the temperature and mass scale, we encounter class K stars, often called orange dwarfs. These stars possess between 60% and 80% of the Sun's mass and boast surface temperatures ranging from 3,700 to 5,200 Kelvin. Emitting a warm, golden-orange light, they strike an ideal balance between moderate radiation output and long-term stability. While red dwarfs are prone to violent magnetic flare activity that can strip the atmospheres of orbiting worlds, orange dwarfs provide a remarkably calm and steady environment. With stable main-sequence lifespans ranging from 15 to 45 billion years, many astrobiologists consider Class K stars to be the premier candidates for hosting habitable worlds and long-lived extraterrestrial civilizations. Continuing upward, we arrive at our home category, Class G stars, traditionally classified as yellow dwarfs. Our own Sun is the quintessential example of this stellar type, specifically categorized as a G2V main-sequence star. These stars typically possess between 80% and 104% of the Sun's mass, with surface temperatures ranging from 5,200 to 6,000 Kelvin. Although labeled yellow dwarfs, they actually radiate a pure, brilliant white light when viewed from space above Earth's filtering atmosphere. Inside a Class G star, the inward gravitational force is powerful enough to demand a vigorous rate of hydrogen fusion to maintain hydrostatic equilibrium. The star operates with an inner radiative core surrounded by an outer convective envelope. At this mass scale, the engine consumes its central fuel supply in approximately 10 billion years. Our Sun currently sits right in the golden middle of this lifespan, having burned through roughly 5 billion years of its fuel reserves, with approximately 5 billion years of steady, reliable light left to deliver. Scaling upward into hotter territory brings us to Class F and Class A stars. Class F stars, ranging from 1.04 to 1.4 solar masses, burn at surface temperatures between 6,000 and 7,500 Kelvin, shining with a stark, yellowish-white light. Class A stars, ranging from 1.4 to 2.1 solar masses, push surface temperatures higher, from 7,500 to 10,000 Kelvin, radiating a crisp, piercing blue-white light. Affiliate celestial landmarks like Sirius, the brightest star in our night sky, and Vega belong to Class A. At these temperatures, the mechanics of nuclear fusion undergo a profound shift. The dominant pathway for fusing hydrogen shifts from the direct proton-proton chain reaction to the carbon-nitrogen-oxygen cycle, a catalytic fusion loop that accelerates dramatically with higher core temperatures. Because energy generation scales steeply with mass, Class A stars consume their fuel at a rapid pace, burning through their entire supply in just 1 to 2 billion years. As we approach the absolute apex of the stellar mass spectrum, we enter the territory of the giants, Class B and Class O stars. Class B stars possess between 2 and 16 times the mass of our Sun, with scorching surface temperatures between 10,000 and 30,000 Kelvin. Shining with an intense, radiant blue light, these celestial titans illuminate entire nebulae, but their blazing output comes at a steep price. Their lifespans are drastically reduced to tens or hundreds of millions of years. Finally, at the extreme summit of the stellar kingdom sit the terrifying behemoths, Class O blue supernovas and hypergiants. These are the undisputed monsters of the cosmos. Possessing anywhere from 16 to over 100 times the mass of the Sun, their surface temperatures exceed 30,000 Kelvin and can soar beyond 50,000 Kelvin. They do not merely glow, they unleash a savage blizzard of ultraviolet radiation and furious stellar winds that blast outward at thousands of miles per second. A single Class O star can produce more energy in a few seconds than a red dwarf generates in thousands of years. Its luminosity can easily exceed hundreds of thousands or even millions of times the brightness of our Sun. Yet this unimaginable power is inherently self-destructive. In physics, the luminosity of a massive star does not scale linearly with its mass. It scales roughly to the power of 3.5. If you double a star's mass, its energy consumption does not merely double, it increases by more than 11-fold. If you increase its mass by a factor of 10, its core burns thousands of times faster. Consequently, Class O stars are the most volatile, short-lived engines in the cosmos. While a red dwarf cruises gracefully across trillions of years, a blue giant burns through its colossal ocean of hydrogen fuel in a frantic cosmic blink of just 3 to 10 million years. They live fast, burn with blinding fury, and race toward a violent, catastrophic collapse. From the eternal dim embers of red dwarfs to the roaring, short-lived infernos of blue hypergiants, the stellar ecosystem is a masterclass in cosmic physics. Each class plays a distinct and vital role in the grand machinery of the universe, setting the stage for the dramatic transformations that occur when the primary fuel tank finally runs dry. No star can burn forever. For millions or billions of years, a star maintains its stable existence through the precise balance of hydrostatic equilibrium. But eventually, the relentless laws of thermodynamics catch up to the engine. Deep inside the core, the primary fuel tank begins to empty. Every second of fusion has steadily converted lighter hydrogen into inert, dense helium ash. As the hydrogen fuel in the central furnace drops towards zero, the star enters its volatile old age, transforming from a steady generator of light into a dynamic cosmic alchemy furnace. When core hydrogen fusion finally ceases, the outward radiation pressure that held up the immense weight of the star vanishes. Gravity instantly seizes the advantage. The core, composed entirely of helium ash, begins to contract rapidly under its own weight. As it contracts, the gravitational potential energy converts directly into intense thermal energy. The temperature and density of the central core spike dramatically. Surrounding this collapsing helium core is an outer shell of unburned hydrogen. The intense heat radiating from the shrinking core superheats this shell, igniting hydrogen shell fusion. This new, blistering shell of fire burns far hotter and more vigorously than the core ever did during its main sequence lifetime. The resulting surge of outward radiation pressure drives a dramatic physical transformation. It blasts the star's vast outer envelopes outward, expanding the celestial body to hundreds of times its original radius. As the outer layers swell across millions of miles of empty space, they cool down from searing white or yellow to a dull, glowing red. The star has officially left the main sequence to become a red giant. If our own Sun entered this phase today, its bloated surface would swallow Mercury, vaporize Venus, and expand to the very orbital doorstep of Earth. Meanwhile, deep within the center of the red giant, the helium core continues its relentless contraction. When the core density reaches extreme levels and the internal temperature crosses the threshold of 100 million degrees Kelvin, the conditions become extreme enough to ignite a brand new nuclear reaction, the triple alpha process. In this intricate nuclear process, two helium nuclei smash together to form a fleeting, unstable isotope known as beryllium-8. Almost instantly, before this fragile beryllium can break apart, a third helium nucleus collides with it, locking the particles together to forge a stable nucleus of carbon-12. In some instances, this newly minted carbon nucleus captures yet another helium nucleus, creating oxygen-16. Through this helium-burning cycle, the core halts its collapse, establishing a temporary new equilibrium as it transforms helium ash into the fundamental elements of organic chemistry. For medium-mass stars like our Sun, this is the end of the line. Their mass is simply insufficient to generate the crushing gravitational pressures needed to push temperatures past 600 million degrees Kelvin. Once the core helium is exhausted, the star cannot ignite carbon or oxygen. The core contracts into a dense, inert cinder, while the pulsating outer shells are gently puffed away into space, drifting outward as a luminous planetary nebula. However, for massive stars, those possessing more than 8 times the mass of the Sun, the story does not end with carbon and oxygen. These massive cosmic engines possess the crushing gravitational force required to smash through every subsequent thermal barrier, transforming the dying star into a multi-layered, onion-like chemical refinery. When the core runs out of helium, gravity crushes the carbon-oxygen core inward once more. The temperature surges past 600 million Kelvin, igniting carbon fusion to produce neon, sodium, and magnesium. When carbon is exhausted, the core contracts again, driving temperatures beyond 1.5 billion Kelvin to ignite neon fusion. Neon breaks down and recombines to form oxygen and magnesium. With each subsequent fuel cycle, the physics becomes increasingly desperate and the timescales shorten drastically. A massive star might spend millions of years burning hydrogen, but its carbon-burning phase lasts only a few hundred years. The neon burning phase is consumed in a matter of a few years or months. As the central core continues its cycle of collapse and reheating, the temperature exceeds 2 billion Kelvin. At this hellish point, oxygen nuclei fuse together in a rapid, furious burn, synthesizing silicon, sulfur, and phosphorus. The entire oxygen core can be exhausted in less than 6 months. Finally, the silicon core contracts and the internal temperature climbs to a staggering 3 to 4 billion degrees Kelvin. Under these extreme conditions, silicon burning begins. This phase is characterized by a violent, chaotic process known as photodisintegration and alpha particle rearrangement. High-energy gamma-ray photons literally break apart some silicon nuclei into helium nuclei, which then rapidly fuse with remaining silicon and heavier elements in an accelerating chain reaction. Silicon fusion builds upward through the periodic table, producing nickel-56, which quickly undergoes radioactive decay into cobalt-56 and ultimately settles into iron-56. The silicon burning phase is so intensely hot and fast that it consumes the entire core of the star in less than a single day. At this stage, the interior of the massive supergiant resembles a colossal onion made of burning nuclear shells. The outermost layer is composed of unburned hydrogen, followed deeper down by shells of helium, carbon, oxygen, neon, and silicon, all burning simultaneously at different depths and temperatures. And at the absolute center of this cosmic titan sits a dense, dead, growing core of pure iron. It is here that the star encounters the ultimate impenetrable wall of nuclear physics, the iron peak. Throughout the entire life of a star, every fusion step from hydrogen to silicon has been an exothermic reaction. Because the binding energy per nucleon increases with each heavier element up to iron, fusing lighter nuclei into heavier ones releases excess mass as radiant energy. This released energy is what created the outward thermal pressure that fought off gravitational collapse. However, iron 56 possesses one of the highest nuclear binding energies per nucleon of any atomic nucleus in the universe. Iron is the most tightly bound, stable atomic structure in nature. Because of this unique nuclear stability, you cannot extract energy by fusing iron. When you attempt to fuse two iron nuclei together, the reaction does not release energy. Instead, it is endothermic, meaning it actively consumes and absorbs thermal energy from the surrounding core. The moment the stellar core fills with iron, the engine stalls. The nuclear fire cannot generate an outward push. Instead of producing heat, any attempt to fuse iron sucks energy directly out of the central furnace, causing the core temperature and pressure to plummet instantly. The inward gravitational force, generated by the colossal weight of all the outer layers bearing down on the center, remains absolute and unyielding. With no outward radiation pressure left to oppose it, the delicate balance of hydrostatic equilibrium that sustained the star for millions of years collapses in a fraction of a second. The stellar engine has reached its thermodynamic dead end, setting the stage for the most catastrophic and violent implosion in the universe. While we often picture a star as a solitary beacon, burning quietly in the dark, our own sun's isolated existence is actually an exception rather than the rule. Across the vast expanse of the cosmos, the universe rarely builds its engines in isolation. Stars are inherently social entities, born together in crowded nurseries and bound to one another by the invisible, inescapable web of gravity. From intimate cosmic partnerships to sprawling stellar metropolises containing millions of blazing suns, the gravitational choreography of multiple star systems forms the fundamental architecture of galaxies. More than half of all sun-like stars and over 80% of massive stars exist in gravitationally bound multi-star systems. The most fundamental of these arrangements is the binary star system, where two stars orbit around a common center of mass, known as the barycenter. In these celestial pairings, orbital mechanics dictate a mesmerizing dance governed strictly by Johannes Kepler's laws and Isaac Newton's universal gravitation. In a wide binary system, the two stars are separated by hundreds or thousands of astronomical units, orbiting each other over millennia with minimal physical interference. Each star evolves almost independently, undisturbed by its companion's presence. But when binary stars form in close proximity, their relationship becomes dynamic, chaotic, and sometimes predatory. In a close binary system, the gravitational fields of the two stars interact to create distinct, teardrop-shaped regions of gravitational dominance known as Roche lobes. The boundary where these two gravitational wells meet is the inner Lagrangian point, a neutral gravitational gateway between the two stellar bodies. As the more massive star in the system exhausts its core hydrogen fuel and swells into a red giant, its outer layers expand dramatically. If the star swells beyond its Roche lobe, its outer gaseous atmosphere is no longer gravitationally bound to its own core. The excess gas spills across the Lagrangian point, tumbling into the gravitational grip of the smaller companion star. This process leads to a dramatic cosmic phenomenon known as stellar vampirism or mass transfer. The receiving star cannot absorb this torrent of falling plasma instantly due to the conservation of angular momentum. Instead, the stolen gas spirals into a blazing accretion disk around the companion star, generating intense friction, ultraviolet radiation, and powerful X-ray flares. In some extreme scenarios, the mass transfer is so rapid and overwhelming that the two stars become enveloped in a shared sheath of boiling plasma, forming a contact binary or a common envelope system. Over time, friction inside this shared gas cloud saps the orbital energy of the two stellar cores, spiraling them closer and closer together until they inevitably collide in a luminous red nova, merging into a single, hyperenergetic stellar giant. Gravity does not stop at pairs. The cosmos frequently constructs triple star systems, quadruple systems, and even complex sextuple arrangements. In these intricate multi-star setups, the law of gravitational stability imposes strict orbital hierarchies. A chaotic three-body problem, where three equal-mass stars orbit each other at similar distances, inevitably ends in disaster. The chaotic gravitational perturbations will eventually fling one of the stars into deep space, leaving the remaining two in a stable binary. To achieve long-term survival, triple systems organize hierarchically. Two stars orbit very close to each other as a tight inner binary, while the third star orbits this entire pair from a vast, stable outer distance. Alpha Centauri, our closest stellar neighborhood, is a prime example of this hierarchical harmony. The bright stars Alpha Centauri A and Alpha Centauri B orbit each other in a close 50-year loop, while the tiny red dwarf Proxima Centauri cruises around the central pair in a sweeping half-million-year orbit. When we zoom out further, from small stellar families to massive collective gatherings, we discover stellar clusters. These clusters represent the grand flocking behavior of the cosmos and come in two distinct flavors: open clusters and globular clusters. Open clusters are young, loose groupings containing anywhere from several dozen to a few thousand stars, all born from the same parent giant molecular cloud. The famous Pleiades, or Seven Sisters, is a classic example of an open cluster, sparkling like a handful of blue diamonds against the velvet of space. Because these stars are relatively young and loosely bound by gravity, open clusters are temporary structures. Over hundreds of millions of years, gravitational interactions with passing gas clouds and the tidal shearing forces of the rotating galactic disk gradually tug the cluster apart, scattering its member stars across the galaxy to wander as solitary nomads. In stark contrast to these fragile open nurseries sit the oldest, most tightly packed star cities in existence, globular clusters. Globular clusters are immense, spherical swarms containing hundreds of thousands or even millions of stars packed into a sphere spanning only 1 to 200 light-years across. These ancient cosmic relics orbit in the halos of galaxies, surviving virtually unchanged for 10 to 13 billion years, almost as old as the universe itself. Entering the core of a globular cluster is like stepping into an astronomical wonderland. While the space around our Sun is relatively empty, with the nearest star 4 light-years away, the center of a globular cluster contains thousands of stars crammed into a single cubic light-year. In the night sky of a planet nestled inside such a core, darkness would never fall. The sky would be perpetually ablaze with the brilliant, multicolored glare of thousands of nearby suns, shining brighter than hundreds of full moons. In these hyperdense stellar metropolises, stars do not merely drift side by side, they actively collide and reshape one another's destinies. The gravitational density is so high that direct stellar collisions and close tidal encounters occur on a regular basis. When ancient, low-mass stars collide in the core of a globular cluster, they fuse their remaining fuel into a single, more massive body. This newborn chimera burns with renewed heat and brilliance, appearing far younger and bluer than the surrounding ancient population. Astronomers call these resurrected stars blue stragglers. They are celestial anomalies that defy the natural aging process of the cluster by literally feeding on their neighbors. Furthermore, dynamic friction inside these massive clusters drives a process called mass segregation. The heavier stars and dead stellar remnants gradually sink toward the center of the cluster's gravitational well, while lighter stars are pushed outward toward the periphery. In the congested center, pairs of stars constantly interact with passing third bodies, tightening their orbits and transferring enormous amounts of kinetic energy, functioning as a colossal gravitational engine. From tight binary pairs siphoning plasma across empty space to majestic globular swarms orbiting the galactic halo, gravity binds stars into intricate, evolving collectives. These multi-star architectures demonstrate that the life cycle of a stellar engine is not just an internal battle of nuclear physics, but an eternal, dynamic dance with the stellar community surrounding it. Every engine, no matter how magnificent or durable, eventually runs out of fuel and meets its final destination. But in astrophysics, the way a star dies is dictated entirely by a single supreme variable: its initial birth mass. Mass is destiny. A star with modest mass will quietly sigh its layers away into the void, leaving behind a glowing crystal ember. In contrast, a massive celestial giant will exit the cosmic stage in a display of apocalyptic violence that outshines entire galaxies, tearing open the fabric of space and time itself. Let us first examine the demise of low to intermediate mass stars, those with masses below approximately 8 times that of our Sun. These stars, which make up the vast majority of stellar objects in the universe, experience a relatively peaceful, elegant death. After exhausting its core helium during the red giant phase, a Sun-like star cannot reach the 600 million Kelvin temperature required to ignite its dense carbon and oxygen core. The star enters an unstable evolutionary phase known as the asymptotic giant branch. Without the stabilizing anchor of continuous core fusion, the outer layers of the star begin to pulsate violently, expanding and contracting over cycles of hundreds of days. Thermal pulses, driven by unstable helium shell flashes deep beneath the surface, send massive shockwaves rippling through the bloated, loosely bound outer envelope. Over tens of thousands of years, these gentle but persistent pulses lift the outer layers entirely off the star, blowing them out into the surrounding interstellar space at speeds of tens of miles per second. What remains of the expelled gas expands outward in all directions, creating a breathtaking, glowing structure known as a planetary nebula. Despite the historical name, planetary nebulae have nothing to do with planets. They are glowing, expanding shells of ionized gas, illuminated from within by the intense ultraviolet radiation of the exposed stellar corpse at the center. This exposed corpse is a white dwarf. Stripped of all its outer layers, the white dwarf is the bare, hyperdense carbon-oxygen core of the dead star. It contains roughly 60% of the Sun's mass, compressed down into a sphere roughly the size of planet Earth. The density inside a white dwarf is staggering. A single teaspoon of white dwarf material would weigh more than 5 tons on Earth. At this incredible density, the normal gas laws no longer apply. The white dwarf does not collapse further because it is supported by a bizarre quantum mechanical phenomenon known as electron degeneracy pressure. According to the Pauli exclusion principle, no 2 identical electrons can occupy the exact same quantum state simultaneously. When gravity squeezes matter to such extreme densities, all the available low-energy quantum states become filled. The electrons resist further compression with immense force, establishing a rigid, non-thermal pressure that holds the dying core stable against gravity. Because no nuclear fusion occurs within a white dwarf, it has no internal heat source. It shines only from the residual thermal energy accumulated over its billions of years of active life. Over hundreds of billions or even trillions of years, this stellar ember will slowly radiate its heat into the freezing void of space, gradually cooling and dimming until it becomes a cold, dark, crystalline sphere of carbon and oxygen, a theoretical black dwarf. However, if a white dwarf resides in a close binary system and pulls too much matter from its companion, it faces a very different fate. As it accretes mass, it approaches a rigid physical ceiling known as the Chandrasekhar limit, which sits at precisely 1.44 solar masses. At this exact threshold, the electron degeneracy pressure is completely overwhelmed by gravity. The white dwarf collapses rapidly, igniting a runaway, uncontrollable carbon fusion wave that tears the entire star apart in less than a second. This cataclysm is a Type 1a supernova, a thermonuclear explosion so uniform and intensely bright that astronomers use them as standard candles to measure the accelerating expansion of the universe. Now, let us turn our gaze to the heavyweights of the cosmos, stars born with more than 8 times the mass of our Sun. For these titans, death does not arrive as a gentle pulsation, it arrives as an instantaneous cataclysmic core collapse, a Type 2 supernova. As we explored previously, a massive supergiant builds an iron core at its center. The moment this iron core forms, the star reaches an absolute dead end. Iron cannot fuse exothermically. The instant the core mass exceeds the Chandrasekhar limit, the outward thermal pressure disappears. In less than 1/10 of a second, gravity wins the war. The entire iron core, an object larger than planet Earth, collapses inward at a quarter of the speed of light, shrinking into a sphere just a few miles wide. The collapse is so brutally fast and violent that the atoms themselves are crushed out of existence. Free electrons are forcibly crammed into atomic protons through a process called electron capture, converting them into neutrons and unleashing an unfathomably dense blizzard of high-energy neutrinos. The collapse continues until the atomic nuclei are squeezed together so tightly that the strong nuclear force becomes strongly repulsive and neutron degeneracy pressure suddenly halts the fall. The collapsing inner core hits an impenetrable quantum brick wall and abruptly stops. The outer layers of the star, having begun to free fall inward at thousands of miles per second, slam violently into this newly formed, rock-hard neutron core. The infalling matter rebounds off the core in a titanic shockwave. Coupled with an overwhelming blast of energy from the trillions of trapped neutrinos bursting outward from the center, the shockwave rips through the outer layers of the star, tearing the entire celestial titan apart in a blinding supernova explosion. For several weeks, this single exploding star outshines the combined light of all the hundreds of billions of stars in its host galaxy. In this brief, fiery crescendo, temperatures and neutron densities reach such staggering extremes that nature performs rapid neutron capture nucleosynthesis, also known as the R process. It is inside this supernova shockwave and in the mergers of the remnants it leaves behind that the heaviest and most precious elements on the periodic table are forged: gold, platinum, lead, and uranium. What remains behind in the smoking ruins of this cosmic detonation depends on the mass of the original star. If the collapsing core has a mass between 1.4 and roughly 3 solar masses, it stabilizes as a neutron star. A neutron star is an object of mind-bending extremes. It packs the mass of 1.5 to 2 suns into a sphere merely 12 miles in diameter, roughly the size of a city. A single cubic centimetre of a neutron star weighs hundreds of millions of tons. These stellar corpses rotate at blinding speeds, sometimes spinning hundreds of times per second, and possess magnetic fields trillions of times stronger than Earth's. As they spin, they channel radiation into intense, sweeping beams from their magnetic poles, functioning as cosmic lighthouses known as pulsars. Some neutron stars, known as magnetars, possess magnetic fields so intense that they can physically distort the electron clouds of atoms from thousands of miles away. Yet there is one final, ultimate tier of stellar destruction. If the progenitor star was a true colossus, possessing more than 20 to 30 times the mass of the Sun, the collapsing core is too massive for even neutron degeneracy pressure to stop the fall. The core exceeds the Tolman-Oppenheimer-Volkoff limit, which sits at roughly 3 solar masses. At this point, there is no known force in the laws of physics capable of resisting the inward crush of gravity. The core collapses indefinitely. It shrinks through its event horizon, the threshold where the escape velocity exceeds the speed of light. The matter vanishes into an infinitely dense, zero-volume point of infinite gravitational curvature, a gravitational singularity. A stellar mass black hole is born. Around this tear in the fabric of space-time, time slows down, light is bent and trapped, and the stellar engine undergoes its final, permanent transformation. The engine that spent millions of years pouring light into the universe has now become the ultimate cosmic vacuum, an eternal monument to the triumph of universal gravity. Stars are not merely distant static light bulbs illuminating the void of space. They are dynamic, volatile powerhouses that actively shape, dictate, and sometimes ruthlessly sanitize the environments of the worlds orbiting them. The relationship between a stellar engine and its surrounding planets is a delicate, high-stakes balance. While a star provides the continuous thermal energy and light required to drive planetary chemistry, its violent nature simultaneously poses an existential threat to planetary atmospheres and the potential emergence of life. Every active star continuously generates a stellar wind. This is not a gentle breeze of air, but a relentless supersonic torrent of charged subatomic particles, mostly high-energy protons and electrons, streaming outward from the star's superheated upper atmosphere, or corona. In our own solar system, The solar wind travels across the interplanetary medium at speeds ranging from 200 to over 500 miles per second. This steady stream of plasma acts like a continuous sandblaster, colliding with planetary upper atmospheres and attempting to sweep their gas molecules away into the depths of space through a process known as atmospheric stripping or sputtering. A planet's primary defense against this unceasing stellar onslaught is an intrinsic global magnetic field generated by an active dynamo in its molten metallic core. When the incoming stellar plasma strikes a planet's magnetosphere, the charged particles are deflected around the magnetic bubble, shielding the atmosphere beneath. Earth possesses a robust geomagnetic shield that successfully preserves our dense nitrogen-oxygen atmosphere. In contrast, our neighbour Mars lost its internal dynamo billions of years ago as its small core cooled and solidified. Without a protective magnetic shield, the solar wind stripped away the Martian atmosphere atom by atom over geological epochs, transforming a once warm, wet world with flowing rivers into the frozen, hyper-arid desert we observe today. Beyond stellar winds, stars are prone to violent, erratic outbursts, driven by the twisting and snapping of their intense internal magnetic fields. As plasma roils through a star's convective zone, it drags magnetic field lines along with it, stretching and knotting them into high-energy structures. When these stressed magnetic loops suddenly snap and reconnect, they unleash two of the most destructive phenomena in astrophysics: stellar flares and coronal mass ejections. A stellar flare is a colossal, explosive flash of localized radiation across the electromagnetic spectrum, blasting out devastating pulses of extreme ultraviolet and X-ray radiation. Accompanying these flares, coronal mass ejections violently fling billions of tons of magnetized plasma into space at millions of miles per hour. When a direct hit from a coronal mass ejection strikes a planet, it compresses the magnetosphere, induces severe geomagnetic storms, and bombards the upper atmosphere with ionizing radiation. This high-energy barrage can break apart complex molecular compounds, strip away the protective ozone layer, and expose the planetary surface to lethal levels of biological radiation. This stellar volatility plays a pivotal role in defining the circumstellar habitable zone, colloquially known as the Goldilocks zone. This is the theoretical orbital corridor around a star where the ambient temperature allows liquid water to persist on a planet's surface under adequate atmospheric pressure. If a planet orbits too close to its host engine, incoming radiation triggers a runaway greenhouse effect, boiling oceans into water vapor, which is subsequently ripped apart by ultraviolet light and lost to space, as happened on Venus. If a planet orbits too far, the sparse stellar flux allows water to freeze permanently into global glaciers, locking the world in an eternal snowball state. The precise location, width, and stability of this habitable zone depend entirely on the mass, luminosity, and spectral classification of the host star. Around massive luminous stars, such as Class A or Class F stars, the habitable zone is situated far out from the star, spanning a wide orbital swath. However, as we have seen, these high-mass engines burn through their hydrogen reserves in only 1 to 2 billion years. Because complex biological evolution and planetary stabilization take billions of years, life around these short-lived giants may run out of time before it ever gets a chance to flourish. At the other extreme sit the ubiquitous red dwarfs, or Class M stars. Because a red dwarf emits only a tiny fraction of our Sun's luminosity, its habitable zone is located extremely close to the stellar surface, often within a distance much smaller than the orbit of Mercury around our Sun. While this close proximity provides sufficient thermal warmth, it introduces two catastrophic survival hurdles for any prospective world. First, orbiting in such intimate proximity to a star subjects the planet to immense gravitational tidal forces. Over tens of millions of years, tidal friction slows the planet's rotation until it becomes tidally locked, meaning the planet takes exactly as long to rotate on its axis as it does to complete one orbit around the star. One side of the world is locked in perpetual scorching daylight, while the opposite side is plunged into endless freezing darkness. Unless the planet possesses a thick circulating atmosphere or vast oceans to distribute heat across the day-night terminator, the atmosphere can freeze out entirely onto the dark side, causing total atmospheric collapse. Second, young red dwarfs remain magnetically hyperactive and unstable for hundreds of millions or even billions of years. They routinely unleash superflares and coronal mass ejections that are thousands of times more energetic than anything observed from our Sun. For a tidally locked planet hugging the star inside the close inhabitable zone, these frequent, violent eruptions can completely strip away its atmosphere, evaporate its surface oceans, and thoroughly sterilize the planet long before the star settles into its calm, long-term main sequence phase. This brings astrophysicists to a profound realization. Finding a habitable world is not merely about locating a rocky planet at the right physical distance from a star. It is about finding a world orbiting the right kind of star, an engine that offers long-term stability, minimal flare activity, and a steady, predictable output of energy over billions of consecutive years. Stars are not just creators of worlds, they are the ultimate arbiters of planetary life, holding the absolute power to foster living ecosystems or wipe them out of existence. To truly appreciate the vast story of these cosmic engines, we must look to both extremes of time, to the very first fires that broke the cosmic dark, and to the silent, cold dusk that awaits the cosmos in the unimaginably distant future. Shortly after the Big Bang, the universe was plunged into a period known as the Cosmic Dark Ages. There were no stars, no galaxies, and no heavy elements. The cosmos was filled solely with a pristine, unpolluted mixture of hydrogen and helium gas, along with a trace of lithium. Out of this pure, primordial soup condensed the first generation of stellar powerhouses, population 3 stars. Because these early clouds contained zero heavy elements, they lacked the efficient chemical coolants that allow modern gas clouds to fragment into smaller clumps. As a result, the Jean's mass required for gravitational collapse was enormously higher. Population 3 stars were absolute titans, often reaching hundreds of times the mass of our Sun. Burning with blinding ultraviolet intensity, their roaring fusion engines synthesized the first heavier elements in cosmic history. These monsters lived intensely brief lives, detonating in colossal pair instability supernovas that seeded the virgin universe with carbon, oxygen, and iron, permanently altering the chemical destiny of every generation of stars that followed. Now cast your gaze across the cosmic horizon, forward toward the ultimate fate of the universe. We currently live in the stelliferous era, a golden, radiant epoch where galaxies are rich with cold gas, nebulae are actively collapsing, and new stellar engines ignite on a regular basis. But this glorious era of creation is temporary. With every generation of star formation, a significant fraction of matter is permanently locked away inside the dense remnants of dead stars, white dwarfs, neutron stars, and black holes. The interstellar gas reservoirs are steadily depleted, converted into stellar ash that cannot easily be recycled. In roughly 100 trillion years, the final pockets of cold molecular gas across the galaxies will be exhausted. Star formation will grind to a permanent halt. One by one, the massive blue giants, the steady yellow suns, and the orange dwarfs will exhaust their fuel and die off. Only the thrifty red dwarfs will remain, quietly sipping their hydrogen reserves over trillions of years. Eventually, even the longest-lived red dwarf will consume its last atom of hydrogen. It will dim, contract, and cool into a frozen cinder. The last star in the universe will blink out of existence. The cosmos will slide into the Degenerate era. Galaxies will become ghost towns populated only by the dead, cold remnants of a long-lost golden age. Cooling white dwarfs, slowly spinning neutron stars, and frozen brown dwarfs drifting through an endless pitch-black void. Temperatures across the universe will plummet toward absolute zero as the expansion of space-time continues to pull galaxies infinitely apart. The glorious engines of the universe, which once illuminated trillions of light-years of space, forged the periodic table, and warmed the surfaces of living worlds, will have finally completed their duty. The thermodynamic fires will be extinguished, leaving behind an eternal silent monument to the power of gravity, physics, and light. From the cold collapse of primordial gas to the blazing brilliance of nuclear fusion and the violent beauty of supernovas, stars are truly the ultimate engines of the universe. They are not merely passive spectators in the dark. They are the active sculptors of cosmic evolution, forging every element heavier than helium and breathing life into the periodic table. Every atom of iron in your blood, every atom of calcium in your bones, and every breath of oxygen in your lungs was manufactured deep inside the nuclear furnaces of stars that died billions of years ago. We are, in the most literal scientific sense, the living legacy of these magnificent machines, stardust that has learned to look back up at the cosmos and understand its own origin. Thank you for embarking on this incredible cosmic journey with me today. Keep looking up, stay curious, and until next time, take care.